Okay, so Peterson is here. Now, let me explain this algorithm. This algorithm is good in the sense that it won't have a race condition. Although you have race, we can say that there will be some condition that generate race condition problem. Yes, it won't give you trouble. Okay? Now, this guy, let's say we have two processes. Okay? One of it will call himself process 0. One will call himself process 1. Okay? Now, I will pass in the process ID. You are process 0, then passing 0. I'm process 1, passing process 1. And I will also calculate your opponents. Okay? Who is your opponent? Is 1 minus the process ID. So that means you are 0, then your opponent is 1. If you are 1, your opponent is 0. Okay? Now, how to go on? Let's say I'm a process 0. So ordinary thing is like this. Ordinary flow. I only have one process. I will say that this is my turn. This is my turn in line 8. Also in line 7, I will state that I'm interested to go in to the critical section. Now, this is I'm the only player. So let's check this while loop. Will this while loop so stupid that I'm the only player and get stuck there? I'm the only player, so the process turn is me. I get the turn. The turn is 0, so good. No, it's not good basically. If the value is true, that means that I will block there. Okay? So how about others? It will also check whether your opponent also have stated that he is interested to go in. If yes, I pretend to be the gentleman. Although the turn is mine, okay, I let you go. I willing to get stuck here. Now, if I'm the only player, then this interested flag will be off for the opponent. So if it's off, that means that I won't get freeze in this BC waiting loop. I will finish the end region. Okay? And after finish the end region, that means that the lock has successfully turned. I will go to execute my critical section, and eventually I will leave and try to turn the lock to off by saying that I no longer have an interest. Okay? So this is a basic case. Basic case. Now I go to the complex case. Yeah, how complex is it? Very complex. I introduce some random, not random, I do it on purpose, some location for context switching. Now, the beginning is still we have two guys on the game. Okay. Now this guy make the first move, process 0. Now how to read this? Because of the space is limited in PowerPoint, so I will now watch carefully. If you find this hard to understand, now follow my way now. If you find non-orange, this orange. If you find non-orange, that means that this guy executes this code. And how about this orange? It means that after execute this code, I change some variable. And I don't have enough space. So I put this here. Okay, basically I assume that there is only one guy executing. It's a 0 guy. And it doesn't mean that the process 1 is running and turn the turn variable into 0. No. It means that only this guy is running, and up to line 8. From 4 up to line 8, you'll find one thing. I will state my interest as well as make the turn, okay, from I don't know which value, but suddenly becomes 0. Okay? So I just write the value here. What's next? Next is, again, this piece of code will be executed by process 1. Process 1 try to go in. Okay? Now, process 1 try to go in with one problem. The turn variable will be turned again. Okay? Let's say they repeat the same style, execute up to 4 to x. Okay? So what will happen? It will change the turn variable to 1, but now both processes state that I'm interested. I'm interested. Okay? Now, it seems to be very complex, right? The turner will turn again, okay, and from 0 and turn into 1. Now, let's say this guy process 0 execute, continue the execution, and enter this area. Now, as if the case for straight alternation say that we rely on different values, right? We rely on different values. So here, we also rely on different values. So if that's the case, even though we have the race condition problem, it won't stop us to make wrong judgment. Okay? One more. Who get the process ID, the last update is the process 1. Process 1 make the last update. So process 1 make the turn variable equal to 1. Turn variable update, last guy is 1. So who get in the critical section? Process 0. Because process 1 pretend to be a gentleman, okay, the turn is mine. But I have the responsibility to let you go, okay, and the gentleman. So this guy will say, thank you, I go in. Because the turn variable is no longer 0. I am 0. The process ID is 0. The turn variable is not 0, but 1. Immediately this false. I won't get stuck in the turn. This is the while loop, and I will continue to execute, enter my critical section. I don't write the critical section here because I don't have enough space. Okay? So how about process 1? Will process 1 go in together? No. Because of course they rely on different values. Process 1 will rely on the process number 1. I want the turn variable is equal to 1. Okay? Your statement will give you true. How about the next statement? Our process has declared that he is interested to go in. So basically you will stop there. Keep turning, keep running this code again and again until this guy say that process 0 enjoy the service inside the critical section. Okay, that means you go to the toilet, use the service, okay, and then go out. Okay? So I don't want to make it into a toilet example because this is crazy. Can you find someone stand in the door and watch? Any people want it? You want it? There you go. Okay? Yeah, no, it's not possible, right? You will just raise your race condition, right? You raise in there and lock it. Okay? So there's a little slight difference here. Any question over this flow? If you have a question, raise up your hand. Yeah. Really? No? Yeah? Yeah? No? 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 Good. If no, go home and try to make some context switching cases by yourself. Okay? Usually, I will translate this question into final exam questions. Usually, translate means maybe I give you another code. Maybe another code saying that I no longer become gentleman. Okay, I will change this. So will it satisfy our critical section requirement? Okay, will we have any problems? Or I stay with this code, I give you an execution order. Okay, what will happen? Okay, yeah, that's why I said that this topic is becoming hard. Okay. Go on. So this Peterson solution is good. No one has problem, okay? So if you don't have problem, I give you problems. These two problems, okay, are the issues of Peterson solution, so that later on we won't have any Peterson solution implemented. We will have something which is non-BC weighted. Okay? So why is that? First of all, BC weighting code, wastes power, basically. You're just spinning there, wasting your power, okay? And what if you only have a one core, one CPU? That means that you will stand in the system, keep spinning for some time without any good progress, and let another people to go in, okay? So basically, if you don't have multiple cores, the impact is very bad, okay? The performance. Another problem is, again, one CPU, one core case, okay? This case, we will call it a very similar problem, or what we call is priority inversion problem. Okay? Now, no one should stop you implementing priority scheduling, right? Every kernel can have a choice to have a whether we support priority scheduling. And I don't know whether you are doing a Peterson solution or APC solution. We don't know. Okay? But so happen that you are writing Peterson solution. Now we will have a hidden problem. And the hidden problem is as if you are inverting the priority. So the priority inversion problem is named like this. When a high priority process comes, no matter what kernel is, usually with high priority implementation, it is preemptive. Okay, if it's not preemptive, why it is priority? Okay? And remember this. Then the story goes like this. I have a lower priority, maybe an ordinary process, okay, reach the critical section, and so happen that this low priority process shares some objects with a high priority process. Let's say we have something like this. Now, the problem comes, if this guy is in the ping zone, and suddenly the high priority process comes in and preempt the kernel, saying that I am a higher priority guy. I need to take your toilet sit. You are very horrible, okay? Yeah, you are in the toilet sit. Okay, and there is a high priority guy. Yeah, I don't know why it's a break the lock and go in. Okay? So what will happen next? Because this guy is a high priority guy, very high priority, it will take the CPU immediately, and while it's taking the CPU, horrible thing comes. The CPU is just doing while one loop. Okay? Because the lock itself is a while one, and can this guy break out of this loop? Never, until you reboot the system. Okay? Why is that? Because this low priority process is holding a lock. It's holding the lock, but you are a high priority process asking for the lock. This guy, although we have a high priority process, as if there's no way to execute. The horrible things come with only when we have one CPU and one core. If it's another CPU, okay, it may really may have a chance that this guy will execute. But we only one CPU, one core, no way. This guy will always take the CPU. Okay? So this is a very horrible problem. Okay? That's why people think of another way. Okay? Now, we all know that using user space, this is user space code. Okay? User space solution has a problem. Oh, by the way, there is other issue with this program, but it can be solved. Okay? It's not a big problem. You can think of some solution, but never put it in the final exam because it's gonna be hard for the most people here. How many processes we can support in this solution? 2. How about making it free? How about making it free? Then the code needs some changes, right? The changes is not few, okay? Quite a lot. Who is other process? It's a bunch of guys. The interested detection also tests for a bunch of guys. Okay, so it can be upgraded to multiple process solution. Okay, but it needs some time to do it. So the final solution that implemented in both, not both, all operating system nowadays is called Semaphore. So who invented this is Dijkstra. Dijkstra is not it's the same guy who invented Dijkstra's algorithm, the graph algorithm, the same guy. Okay, that guy do many things. Okay, one contribution in the OS community is the setup of a semaphore. Okay, so what is the semaphore? Semaphore is meaning the flagging signal. Okay, you can see this in an airport, in a train station. Okay, it's called a semaphore. Okay, this semaphore. Okay, it's just a name. Just a name. You don't need to ask, oh, why it's called semaphore. Ask Dijkstra. Okay, but you cannot ask him. He's already dead. Okay, is it? Yes, should be. Okay, so in order to understand what it is, okay, I give you some imaginary code. The design of semaphore is deep down into the kernel. It requires kernel support as if it is a system call. So I will give you some imaginary code to understand this. Now, first of all, what is a semaphore? In my example here, I just treat it as an integer. Okay? So just type that. It is an integer type. As an integer type. And I want it to be unsigned. I want it to be unsigned. Want it to be unsigned. But I don't write unsigned here. Okay? So what is the meaning of want it to be unsigned? Now, let's see what are the two imaginary system call. The first system call, imaginary, okay, is called up and down. Okay? Up and then down. The one and the two. Now we'll focus on the down call first. So in the down call, why I said it's imaginary. Now, first of all, there is a sleep call here. We call it special sleep. Okay? So what is the meaning of special sleep later on we will talk about? It's associated with this special wake up. Okay, so the special sleep will only be wake up with special wake up. Okay? And what else that you have problem with this guy? Yeah, why I highlight is all highlighted there. Oh yeah. Yeah, okay. The problem with Mac, okay. Yeah, so happen I want to highlight disable interrupt. We highlight it's also highlight enable interrupt. Okay. So disable interrupt, you have seen this before. I said that there's an inside kernel. So that's why this is a system call. You ask the system for your service. And this disable interrupt, enable interrupt. So what are the components that you don't know? Yeah, basically I talk about all things here. Now we go to the operations. Anything I miss? You know pointer, right? Yeah, very many puzzle face here. Pointer, okay? Not multiplication. I don't say that, oh, what is semaphore times S? Now the operation comes. So I said that this is a system call. If you create a semaphore through the kernel, then the kernel will have a structure. Remember its value. Every semaphore can have an initialization value. Okay? So later on in different algorithms using semaphore, I will tell you different initialization values. Let's imagine that we are in, I forgot to, why in this set of slides I always forgot about the initialization value? No, sorry, you write down, okay? The initialization value here is 1. Okay, it's 1. Okay? So this initialization value 1, okay, means that I try to decrement the semaphore values. Okay? So let's say this is the first time that this process 1, 2, 3, 4 execute this code. And don't look at this 0. Okay? I want the initialization value to be 1. So what happens if the initialization value is 1? The down call, I color it as red. It means it is the lock. It is the lock. Okay? If I can pass through the entire call, that means that I finished the locking procedure. So let's see how to do the lock. I will first disable interrupt inside the kernel. This is some call. So I disable interrupt. Now we know that it's the most powerful weapon, so no one can stop me. Then I will enter the decision here whether I should go into the while loop. Since I said that the initialization value is 1, so I won't mesh with 0. I will quit this loop and decrement it by 1. That means 1 is unlocked, 0 now is locked, as if I'm using the lock variable. 1 down to 0. So that's why the name is called down. 1 to 0, and then quit it. Before I quit, of course, I have to enable interrupt. This is the pass number 1. Now, pass number 2. Let's say, I don't know why, there is a bad programmer. Also, the process 1, 2, 3, 4. Call the down call again with the same semaphore. So it will down from 1 to 0. Now, what happens if it's 0? I said that I want to keep this value unsigned. Okay? I don't want it to drop into the -1. So if I enter here, original is 1, means unlocked, 0 is locked. You try to lock the door twice. Okay, don't try it on the toilet. Okay, I don't know what will happen. Okay? You try to do it again, you will have a penalty. The penalty is, let's look at here. You will first disable the interrupt. In a while loop checking, now you are 0. You are 0. down from 1 to 0, and you try to further down one more time, 0. Then I will go into enable interrupt again. Why? Because I want to go to sleep. Because the lock is already locked. Okay, you lock it again, I will give you a penalty, you go to sleep. Be blocked. So I will first enable back the interrupt so that I don't carry the interrupt into sleeping state. Yeah, very horrible if I forgot to enable interrupt and I sleep. Okay, you need to reboot the system. Okay. So enable interrupt and then sleep. So how special this sleep is? This sleep is very special. Before I really go to sleep, inside the kernel level, this process knows that I need to be wake up. Okay? So I put my PID inside the structure of a semaphore, and the structure has a list of PID. The list of PID is to state that, hey, when there is another guy, so happen that another guy try to unlock the door, please wake me up. Okay? So imagine that it's outside the toilet, very interesting. There's a lot of dead bodies, okay? Yeah, sleeping on the floor. Okay, don't sleep on the toilet floor, okay? Just sleep there, okay? And waiting for someone to shake him up. Okay? The guy coming out of the toilet is very, very busy. When he come out of the toilet, you shake them all out. Okay? So this is a list. This list, I said this list. That means we can have more than one process waiting for the door to be opened. Okay? Any questions? Should be no question, huh? Because you don't understand. Okay, so let's say during the 1, 2, 3, 4 is being blocked. Other process also being blocked. So let's say this 2, 4, 6, 8 also being blocked here. So two guys are blocking. I said that we allow multiple process inside joining this waiting list. So back to your real life, okay, there is two people sleeping on the toilet floor waiting for the door to open. Very horrible. Now, what's next? I don't know why. There exists a process inside the toilet called 1357, ready to go out. When it's ready to go out, it will call up. Try to bring the semaphore value from 0 to 1. Bring it up. So during the bring up process, we have to do a check. The check is, of course, we have to disable and enable interrupt. During the check, I will look at, are there any people inside this waiting list? If yes, shake them all. Okay? Yeah, shake. Yeah, wake up and wake up. Okay, there's two guys. 1, 2, 3, 4, 2, 4, 6, 8. You both wake up. Okay, I'm out of toilet now. Yes? No, semaphore can go beyond 1. Yeah, later on we will talk about why. Okay? So now we unlock, shake their bodies, yeah, wake up, and we enable interrupt. Why we need to enable interrupt? We want to have timer interrupt again, so that the timer interrupt say that this is the time that you execute, or this is the time you execute. I don't know. Just let the scheduler decide. Okay? So we will have a chance like this. This guy suddenly being wake up, it will look at the code. It's again the down call. Originally, this guy executing down call and being put to sleep. And when it wake up, it will wake up from line 5. We turn from line 5 now. And we enable and we disable again. We disable the interrupt and go back to the loop. Now the loop gives you another value. S is being changed from 0 to 1 again. And this guy will eventually change it to 0. Because I find that after I disable the interrupt, no one can disturb me. I look at the S value, previous guy, change it to 1. So I can decrement it to 0. Yeah. So that means that those guys being put to sleep, when they wake up, it will immediately try to grab the lock. Okay, so this is automatic, grab the lock. And when this guy successfully grab the lock, okay, this guy successfully grabbed the lock. How about this guy? Sorry, later on, this guy, yeah, because you love to sleep on the correct floor, okay? You wake up later, then you'll find that special sleep return, call disable interrupt, and find that, oh, S is 0 again. Yeah. Sleep again. Yes. Yes. Yes, it's the one we call the up. Yeah, to call it up and then turn the semaphore values from 0 to 1, and that's why other people wake up. The guys wake up is returned from this line. So that's why it will immediately continue to do the check. That's 357做唔到嘢。Who? This guy? Or this guy, it may not try to execute code inside critical section again. If it wants to execute code inside critical section again, it needs to call down. That means the entry. Okay. Yes? Then what's the problem? No problem, no problem. Because it's already exit. It wants to exit. So if your argument is after I re-enable interrupt, immediately switch to 1, 2, 3, 4. And 1, 2, 3, 4 grab the semaphore value, change it from 1 to 0. Then what happened to this guy? This guy has no problem because it's already the exit. Yeah. Yeah, imagine you put your mindset back in the toilet, then you understand. Yes, because the last line is enable interrupt. Yes, if the interrupt enable, the scheduler can work. Else the scheduler cannot work. Because there's no time interrupt. Any questions? Yes?
How does the program avoid the two process awake at the same time?
Good questions. There can be. There can be both processes wake up at the same time. So that's why the enable interrupt is not that simple. The enable interrupt also has to guarantee that there's only one guy can enable the interrupt or disable the interrupt. Yeah, this is something special. Yeah, good questions? Any other questions? Yes?
Why do we need to check whether the S is equal to 0? Because I think when there is process using this.
Oh, so that means that you don't want to if. You don't want to if and call special wake up unconditional.
No, I think S must be 0.
No. I didn't say what is the initialization value of semaphore because semaphore can be a bigger number than 1. Yeah, if semaphore starts with 3, then I call down, it becomes 2, and then 2 I call up again, it becomes 3. Yeah, up contains a line increment the x. So if it is from 2 to 3, 2 up to 3, we don't need to wait for anyone. Later on we will explain this, don't worry. Any questions? Yeah. Yeah, don't take it, I said this already, it's some imaginary code, but don't take it as a joke. This is how it implemented inside the kernel. I check the code and write this imaginary code, yes? Yes, 0 means lock. Yes, other values means unlock. Any questions? No? Good. Good, then I can set up examination questions. You said you understand. Okay, so what will happen if we use up call and down call to implement entry and exit? The code will become something like this. Down is the lock, up is the unlock, and with the S value, initialization value is equal to 1, okay, we call it binary semaphore, either 0 or 1. 0, 1, 0, 1, so it's binary. I will first check whether I can go in. If it's 1, I go in. And while I'm taking the lock, S will become 0 at this point. Other process, if it's execute this code, will be being blocked there because the S value is 0. Okay, I can have multiple processes being blocked together. no problem. These two guys block together. When S is equal to 1 by using the up call. Now remember, when up call is being activated, basically you will shake these two guys, hey, wake up. Both of them will wake up. And it is the problem of the scheduler, the business of the scheduler, to decide who will execute his code first. If this guy executes first, you will have this schedule. If the later guy executes first, we will have another schedule. Okay? This is semaphore. Okay? And this will be our last choice. Other choices, okay, because this is using a PC waiting, okay, there is some problem that we cannot avoid. So Dystron came up with the last solution, and it is all implemented inside the kernel. Okay, if you have heard of database lock is implemented using semaphore. If you are using, if you already know thread, okay, the thread internals are all implemented using semaphore. Okay, and in the next week, okay, I will skip this. I will delete this page. This page is not good enough. I delete this. Okay, in the next week, we will talk about something called classic IPC problems. So what are the meaning of classic IPC problem? Go back home and push the up and down call inside your thread. Because we will always use the up and down call to implement 3 solutions. 1, producer-consumer with multiple producer and multiple consumer. Okay? Pipe is 1 producer and 1 consumer. How about multiple? Dynamic philosopher. Okay, the name itself is funny, but it is not a funny implementation. Okay, the implementation itself is very horrible, and you can use it to implement cross-road traffic light control. Okay, no matter how many roads is come together, you can implement this control using dynamic philosopher. The last question, we call it writer-reader or reader-writer. Okay, problem is to guarantee high concurrency for reader. Say you always access a database using Semaphore, no updates. So why not we allow concurrency? You can both read together. No need for mutual exclusion. But what if I suddenly have a writer? Okay, so the database topic. Now, why I stopped earlier, we have a midterm event.